So this is EDA tutorial number 2. Close it. I'll first open my terminal, enter my project folder, ICFB, and let me also open up the EDA tutorial task. So we are going to build up this amplifier, and the size of the amplifier is based on the numbers specified here. And here, like originally, my plan was to use 1 micron as a width, but the minimum, the resolution of this process doesn't allow 8 micrometers, so we use 7.95 micrometer, and this multiplied by 4 means we have 4 fingers altogether. So the total width of the transistor is 8 times 4, which is approximately 32 micrometer, and the length is 2 micrometer for this guy, and this guy. Okay. And for P0, P1, P0 is this transistor, and P1 is this transistor. So the size is 8 times 2, which is 16 micrometer for the width, and the length is 1 micrometer. And the reason I break down this 16 micrometer to 8 times 2 is for the convenience of layout. So later on, when we learn layout, we'll see how important it is to break down the width. If you have a very long transistor, like 32 micrometer, and the length is only 2 micrometer, it looks weird. It's gonna be very long, something like this, right? And that is not good. So we have to break down using multipliers in our process. So for the details of how to use multipliers, we will cover it in layout. So for now, we just need to know that 8 times 4 means the total width is 32. Okay, and we also have transistor N0, N1, and transistor N3. Size is also given here. Okay. And one thing to be noted is I can't change the size of N3 to an arbitrary number, because as we learned in our class, we want a good match between the left branch and the right branch of the differential pair. And that means the VGS of N3 has to be the same as VGS of N1. So based on that, we have to determine the size of N3. Does this make sense? Okay. And eventually, after we get this amplifier, we add some port and build up this symbol for the amplifier. And on my test bench, I'll use this amplifier symbol, and I will configure the amplifier in a certain feedback loop to build up the real application. So basically, in this EDA tutorial, we are going to have 2 schematics files. One is the operational amplifier itself, and another is test bench. And after that, we have to do simulation, and we have to determine the size of the capacitor, compensation capacitor, and resistor, so that we have a good phase margin. In Cadence, we can use stability simulation to figure out what is the phase margin of the amplifier designed. So eventually we have to simulate the loop gain, the phase margin, as a function of temperature. Alright, this is my Cadence library. So for today's demo, let me build up a new library, because I already have one built in my original library. So EDA demo, this is my library for class demonstration. Click OK, and I have to attach it to an existing text file, which means I have to relate the design to certain process. And here from the drop-down list, I have to choose AMI06. Click OK. So So now I have this library set up, EDA_demo, and my first cell. So go to File, New Cell View. My first cell will be the operational amplifier itself. So I'll name it as OP-AMP, operational amplifier. And it's gonna be a schematic view. Click OK. And if you are doing this, you are following me, feel free to let me know you have any problem, you can't find any button on my screen, or you want me to stop to talk a little bit more. Okay, so suppose you should have this schematic here, and now our task is to put the transistors into the schematic. So I'll use the button I, which stands for instance, to add instance, and on the library I have to choose NCSU analog parts, and from there we can find out N transistors. So I'll add NMOS 4, which means 4-terminal NMOS transistor. Put it over here, and if I hit a button of F3, it will bring. Oops. If I copy the transistor and hit a button of F3, it will bring up this property window for copy. So I will choose sideways. See, currently this transistor is arranged in this orientation. If I click sideways, it will be flipped. Right? Does this make sense? Okay, and I can put it here. After this, because I'm always lazy, then I hit a button of M to move this transistor a little bit. See, the wire will be generated automatically. Right? Can you follow me? Okay, and now I choose this transistor, and I hold my button of Shift, which is similar to what we did in Windows, right? Then I can choose multiple components. After I choose those two, I use the button Q. Q stands for property, and bring up this window. And from there, I can change the parameter of the transistor. So first, let's check. For those two bottom transistors, N0 and N1, the size is given as 8 × 2 micrometer as the width, and the length is 1 micrometer. Okay, so for the multiplier, I have to use 2, which means multiply by 2. And for the width, I'll change it to 8 micrometer, and the software will automatically round it to 7.95 micrometer, which is supported by this technology. You can imagine that you can't ask the foundry to fabricate an arbitrary number, right? So there's gonna be some number that is supported by the foundry. And for the length, I'll change it to 1 micrometer. So it will be automatically rounded to 1.05 micrometer. That can be fabricated by the foundry. So after that, I double check. The width is now 8 × 2, and the length is 1 micrometer. So everything looks okay. But one more thing, very important. Since I'm trying to change the property of the two instances altogether, I have to go to the top of this window and change apply to from only current to all selected. All selected means I change the property of all the selected instances. Does this make sense? Okay, so I click OK. After that, I hit button F to zoom in, and we can see that now the width is changed to 8 micrometer. M equals 2, which stands for multiplier is 2. So the total width of the transistor is now 16 micrometer. And the length, L, is 1 micrometer. Does this make sense? Okay. Okay. Right here, the width is 8 micrometer. That is a single multiplier, and you have two multipliers, M equals to 2. So the total width is 16 micrometer, right? And the length is 1 micrometer. Okay, and the next I want to add this transistor, N3, and N3 is twice as big as N0 and N1, so I copy it to this side. I bring up the property, use button Q. Oops. Choose this instance and hit the button Q. And scroll down. So now, since N3 is 2 times as N0 and N1, I have to change the multiplier to 4. Okay. So now the multiplier M is 4, right? And I have to make the wires. And for the NMOS, remember, the body can only be connected to ground. So for the body terminal, I'll connect them to the ground. Okay, so basically that's 3 transistors on the bottom side. And on the top side, I have 3 PMOS transistors. So now, since I'm lazy, I don't have to find out the components there. I know that the NMOS cell name is NMOS4, so I'll guess that PMOS name is PMOS4. Okay. So after that, I have to change the property of PMOS. Yeah, it's amazing that every time if I do EDA tutorial, it works slowly. Okay, so PMOS, first for the width, I'll change it to 8 micrometer. And for the top 3 PMOS, the size is 8 times 4. So the multiplier will be 4. And the length is 2 micrometer. And can anybody guess why for the top 3 PMOS the length is larger, 2 micrometer? This we will learn in our next lecture. Basically, if the size is larger, then it means the transistors probably they suffer less from process variation and mismatch. Imagine that if you fabricate a bigger transistor, then you can make it more accurate. The error will be relatively smaller, right? And the top 3 PMOS transistors, they are nothing but current mirror. So we want good mismatch, and we want good. We want to minimize the process variation, and that is why for the top PMOS, the length is larger. So we just need to make the connections quickly. Okay. And now I have to add the differential pair. And the differential pair is a PMOS transistor. So I add them like this. And for the differential pair, the size is 8 times 2 for the width and 1 micron for the length. So I change the multiplier to 2, and I change the length to 1 micrometer. and I copy the transistor to the other side and make the basic connections. Okay, and for PMOS, because the PMOS body is built up by isolated N-well, so we can connect the body of PMOS to a different voltage. Okay, and I make a connection here, and I make a connection from the differential output to the second stage input. And right here we have to make a connection for the current mirror. And basically that's all needed for the amplifier. Okay, and I have to make the diode connection for the current mirror, right? After that, I have to add the pins for input and output port. So I use the button P. P stands for pin. And for the pin name, first I have to add the VDD and the ground, the supplies. So I add VDD underscore chip and the GND underscore chip, which stands for the VDD and ground for the on-chip design. And I have to change the direction from input to input output. Okay, so I put the VDD chip here, and I put the VDD ground here, and I make a connection, add wire, like this. Okay, and I continue to add pins. I have to add I reference, input plus, input minus, and those are the input pins. So my reference current is added here. And which side is the plus, input plus? Left or right? It's gonna be the right, because this is a two-stage amplifier, one inversion, two inversion, right? So, and I can use the right button of my mouse to rotate this pin so that it looks nice. The character is on the right side of the pin, and I rotate it again like this. So those are the input pins, and the last pin I have to add is the output pin. Okay, all right, so this is my amplifier. And after I save it, it tells me there are two warnings, and the warning are already highlighted. So look at this, what's going on here? What's the problem? We are missing the current mirror, right? For differential pair, the load, we need to use diode connection for one side. Does this make sense? Okay, great. So now save it. Everything looks fine. Can you guys follow me on your computer? Great. Okay, so the next thing is, after we have this circuit, the point is we don't want to add the signals, add the supplies on the same schematic, because this schematic stands for what I have on chip. I designed for the CMOS chip, and for the signals, for the supply, power supply, those are off chip, right? So I have to separate them. So now I go to design, create cell view, from cell view. Basically, I want to create a symbol for this to represent my on-chip design, and I click OK. Can you follow me on this? So go to design, create cell view, from cell view. Then you just click OK. So this is the symbol of the amplifier I have built. The inputs are on the left side, in plus, in minus. I reference, and output is on the right hand side. And we have VDD, GND. And normally I'll change this symbol to make it nice so that people can easily identify, other designers can easily identify what did I design here. So I can delete the green box first, then I click this button, the button over here, to add line, and then I can manually draw the shape of this symbol. So this looks closer to an amplifier, right? And I can move the eye reference to a different location, to here, and move the character here. And for the input, make it nice, and move the output a little bit. If you don't have enough time to change it, you can just watch this and change your symbol later on after class, because this doesn't affect the function, it just makes the design more professional. Okay, and this is my VDD chip. And this is GND chip. Okay. And in some companies, you are required to do this, because if everybody uses the default rectangle box, then things get messy and you don't know what's going on in the higher level design. Okay, so this is the symbol, and now I save it, I close it, and on the schematic, original schematic, I also save it, I close it, and I go back to the library manager. And now I have to create a new cell view, the test bench. So I name it as EDA2_TB, and TB stands for test bench. Click OK. So on the test bench, what I can do is I can hit the button I to bring out the instance window. And the interesting thing is, if you go to library, you can find out the library that you designed, EDA. In my case, it's EDA_demo. And there we can see this cell we designed, the op-amp. So I choose this, and I move my mouse to the schematic. Then I can add this amplifier, right? Okay, so this is what I designed for the CMOS chip. And now I have to add the signals and the bias to test it. So I hit button I, and I change the library to analog lib. L has to be capital, okay? And for the cell, I'll type VDC to add DC bias. And in this example, we assume that we have 5 volt supply voltage. So I set DC voltage to be 5, and I put it here, add my ground. So I'll change the cell name from VDC to GND, which stands for ground, and I put the ground on the schematic. Move it a little bit, and now I add an inductor. And for the inductor, I'll set the inductance to be approximately 1 nanohenry. And I add inductors here and here. And I make some connections. So the 2 inductors, they are both 1 nanohenry. And now I use the button L. L stands for label, to label the net. So after L, I type a wire name as VDD_chip. Let's use a different name. VDDC and the GNDC_C. Okay, let's do this. I name the 2 nets as VDD_C and GND underscore C. I can use a space between them. Then now I move my mouse into a schematic. I click the first wire here. And now this wire is named as VDD underscore C. And the other wire is named as GND underscore C. Okay. Can you follow me on this? Okay. And likewise, I add 2 wires for the supply of the amplifier. And I name them as also VDD underscore C and GND underscore C. So if we do this, it means this wire is named, actually this wire is on the network of VDD underscore C, and here this wire is also part of the network of VDD underscore C. So it means we have a physical connection from here to here. Does this make sense? Okay, so this is convenient. In the future, you don't have to draw a lot of wires. You can simply name them to tell the software they are connected physically. Okay, and what does the 2 inductors mean? Let's guess. We have 2 inductors. The inductor stands for the bond wire. So if you fabricate this chip, you have to make a connection from the chip to the pin of the package. And the package is going to be the so-called chip you use in experiment. Like you order a chip from Texas Instruments, you're going to have the package, plastic package with several pins, right? But inside it, you have the semiconductor chip. So you have to make a connection from the semiconductor chip to the pin of the package. And then you have to use the bond wire to make the connection. So bond wire, basically it's a metal wire to connect the pad from the pin. So I can use Shift N to add a node. Shift N, add a node. This is bond wire. And normally I'll change the size to be a little bit bigger. And I write it here. So this is a bond wire. And I can also use N to add a box, dashed rectangle box, to highlight this and tell others this is my bond wire. So basically this models the package. Okay. And for the input, I'll continue to add some VDC as the input, DC voltage. So in this EDA tutorial, our DC voltage is going to be 2 volts, which is a common mode bias voltage for the input plus and input minus, right? So I connect them like this. And I add my ground here. Does this make sense? Okay. And for the output, name it as out. Simply name this as out for the convenience of analysis. And for the reference current, it's 20 microamp, so I add IDC. Add IDC and change the DC current to 20 microamp and make a connection here. And also give a ground, otherwise there's no way for the current to flow through. Okay, does this make sense? So this is my top level test bench. And now I check and save the schematic. It gives me another warning. Okay, 2 warnings found. And if you want to know the warning information, you can actually hit the button G. And then it will tell us the out here is floating. Nothing is connected to out. Okay, if this happens in the future, what we can do is you can hit button I to add another instance. Under library basic, you can add no CONN, which stands for no connection. and I put it right here. So this one doesn't affect the electric performance. It only tells the software I intentionally leave this out. I mean, there is no connection for the output port. Okay. Without this, you are gonna have 2 warnings, but you can still simulate it. And if you add this, you will have no warning. Okay. So after that, pretty much I have all the schematic, and I go to Tools, Analog Environment. So this window, very frequently in the future, we will call it ADE, because it stands for Analog Design Environment. I go to Setup, Simulator, and I'll change the simulator to Spectre, which is pretty much the most popular simulator given by Cadence. Okay, and I go to Setup, choose Model Library, and if you remember, we can actually choose Browse and go to the folder Model and select the model for the NMOS transistor, NFF. No, let's use NTT typical and add it. And we have to find out the model file for PMOS transistor, which is ptt.typical. Add it. Click OK. All right, and after that, I have to go to Analysis, choose DC. So I'm gonna do DC operating point simulation, and I want to save the DC operating point. Enable this, click OK, and in case the software just crashes, I'll go to Session, Save State, and I'll save the setup. Click OK. All right, after that, I click this traffic light button to run the simulation. And I'm lucky here, there is no problem. So simulation is finished, total time required. So this means the simulation is finished without any problem. Close it, go to Result, annotate DC node voltage. So now you can see the DC node voltage 0 volt, 5 volt, input 2 volt, input 2 volt, which makes sense, right? And how can we check the operating point inside this? We have to select the op amp and use the button Shift E, and now click OK. So we descend into this hierarchy. And here we can also go to Result, annotate DC node voltage. So DC node voltage is shown here, and we can also annotate the DC operating point. So with this, we have to check the transistors one by one to see if they are operating in active region. And the answer will be yes. So every transistor is working in active region, and we can check if the current makes sense. We have 20 microamp of current as a reference in right here, and this branch we get pretty much also 20 microamp, a very good current mirror, right? And this branch we get 22 microamp. And the reason this one has a larger error is because this voltage, output voltage, is currently 1.3 volt, which is very different from the voltage here. So this transistor and this transistor, they don't have the same VDS, and you suffer from the channel length modulation. So there is second order effect, some error, right? But generally speaking, this is a good current mirror. We mirror the 20 microamp current to this branch and this branch. And if you check the differential pair, each transistor will have 10 microamp of current, right? And another good thing is if we check the voltage here and the voltage here, they are exactly the same, 851 millivolt. So the differential pair is balanced, right? Okay. Anybody can get the same result on your computer? Never mind, you can continue to finish it after the class. So one problem we have already seen, the output voltage is not very nice. The output voltage is 1.3 volt. It's closer to the ground and further away from the VDD. VDD is 5 volt, right? So, and actually it's difficult for us to tune this voltage right now because we have a very high gain from here to here, right? And this is one example to demonstrate open loop amplifier doesn't work very well. So our next thing is to add a feedback loop. Okay. All right. Sorry, before we add a feedback loop, we can do another thing. Sorry. We can, at the input side for positive in, we can, for this signal source, we can add AC input of 1 volt. So that means here, for this signal source, we not only have 2 volt DC bias, but we also have a small signal in AC as 1 volt. And one thing to be noted is when Cadence simulates the circuit, if you tell it we are doing AC simulation, then it's analyzing the small signal performance. So although I'm crazy, I told it 1 volt is my AC signal, it doesn't care. It still analyzes the circuit as a small signal circuit. So AC simulation, if I give it 1 volt, the output will be 1 volt times the AC small signal gain from input to the output. All right? And the reason I choose 1 volt is 1 volt is really convenient. If I have 1 volt of AC here and I measure 10 volt of AC at the output, then it means I have 10 times of voltage gain, right? And that means we have 20 dB gain. Very convenient. So here I'll go to analysis, I'll add another analysis, AC analysis. And for the AC analysis, I'll do frequency sweep from 1 Hz to 1 GHz. Click OK and start the simulation. And the simulation is finished again. And now we can go to result, direct plot, main form. From there, we can plot the AC voltage and we can convert it using dB20 operation to calculate the dB scale gain, right? So if I click the output, it means we calculate, we plot the output voltage, AC voltage, and we convert it using dB20. So I click this, and now this is the result. So this tells us at low frequency, around 1 Hz, the gain is pretty much look at the left top of the window. The Y number you can read out is 77, which means the AC gain, the small signal voltage gain is 77 dB. Does this make sense? Okay, and if we move the mouse, you can see that the gain will drop, right? And currently the gain is 45 dB. I'm talking about the number over there. Okay. So this is the amplitude, the magnitude of small signal gain. We can also plot the phase. We can also plot the phase of the output signal. And now I move the mouse to the schematic and I click the output net, and this is the phase. And I can use this button, switch the axis mode. If I click this button, I'll have 2 different coordinates. So the first curve, this one, is the phase of the small signal gain, and the other one is the magnitude in dB. Okay. If we want to find out the phase margin, then what can we do? We can add marker A, and on the gain, we have to find out the gain crossover point. Is that right? Okay, so I'll try to find out the gain crossover point, and I I read the number on the top left corner. So now the number is very close to 0 dB, right? So this is the gain crossover point. And the gain crossover frequency, is shown on the left, bottom left corner. It's 355 megahertz. And I can add another marker, marker B, to be at the same frequency, but I add this marker on the top curve to read out the phase shift. Does this make sense? So I'll move this marker B also close to 355 megahertz, and we can read out the phase shift, and the phase shift is negative 210 degree. So is this amplifier gonna be stable or unstable? Unstable, obviously, right? Because the phase shift starts from 0 degree, and now it's negative 210 degree. It's unstable. Great. So next thing is we have to learn how to compensate for it in a real feedback circuit. So in a real feedback circuit, I'll delete this, and I'll make a connection from the negative in to the output. So what is the function of this amplifier right now? From here to here. It's a voltage follower, right? A buffer. And the gain will be 1. Great. And a good thing is Cadence, if we have this feedback loop, it's going to be difficult. It's going to be inconvenient to simulate the phase and the gain and also phase margin using AC simulation. So Cadence gives us a more powerful tool. We can use the stability simulation. So in order to do stability simulation, first I'll delete the setup for the AC signal in at the input side. So now we only have a 2 volt DC here. And in order to do stability simulation, I have to insert a probe, stability probe. So for the stability probe, we use analog library, and we use the component of VDC. So VDC is actually a DC voltage source, right? But if we set the DC voltage to be 0 volt, then we insert it into the feedback loop like this. It doesn't affect the performance. Does this make sense? 0 volt ideal voltage source, it doesn't affect the performance. But now we can use this as the probe to test the stability. So I go to analysis, choose, and I'll choose STB, stability simulation. For the frequency, I'll sweep it from 1 Hz to 1 GHz. And now on the bottom side, I have to select the probe instance. So I click select, and I go to schematic. I choose this 0 volt voltage source. So now if you look at the setup of STB simulation, the probe instance will be /V3. V3 is the number of that voltage source. So I click OK. After that, stability simulation is added to the analysis. I'll save my state first. So now I click the traffic light button to run the simulation. And the gain simulation is finished. If you look at the log, everything looks fine. Okay. And now I'll go to result, direct plot, main form, STB. And on the STB, it's chosen as loop gain. And I plot the magnitude and phase. And for the magnitude, I'll convert it into dB scale using dB20. So I click plot. Now we have both the magnitude of the loop gain and the phase of the loop gain. Does this make sense? And the curve looks very similar to what we got in the AC simulation, but it's gonna be different. And the reason it's different is because now the DC operating point is different. With this setup, what's gonna be the DC voltage here for the output? It's simply 2 volt, right? So if we go to this amplifier and check the voltage, now the output DC voltage is 2 volt, exactly 2 volt. So the operating point is a little bit different, so the result will be a little bit different. Okay, so this is the loop gain and the loop gain phase. And in this case, what is the value of beta? Beta is simply 1, right? So the plot of the loop gain and loop gain phase actually stands for the gain and the gain phase of the operational amplifier itself, because loop gain equals to the amplifier gain multiplied by beta, right? And beta is 1 in this case. Okay, and let's see. Oh, another very nice thing is you can go to result, direct plot, main form, and here instead of choosing loop gain, you can choose phase margin. And if you choose phase margin, it tells us now the phase margin is -44 degrees. And this means the amplifier is unstable, right? Phase margin, we want a good phase margin, a positive number, and it's going to be large in order for the amplifier to be stable, right? So this is not stable, and the phase margin is very bad, -44. Click OK. So what we can do is we can add that compensation capacitor, right? The Miller compensation capacitor between the output of the first stage and the output of the second stage. So add a capacitor here. So I'll click button I, add instance. I'll type CAP, which represent capacitor. And for the capacitance, I'll use 2 picofarad. Don't make this too big because it's unrealistic to realize a very large capacitor on chip, right? So 2 pico is already pretty large for on-chip design. So I add this 2 picofarad capacitor and I run the simulation again, see if there's any difference. So simulation is finished. I go to result, direct plot, main form, and I first want to know what's going to be the phase margin now. And now the phase margin is 70 degrees. Very obvious that's different, right? And I can plot the loop gain. So I go back to the waveform window, click this button, add the sub window. So this is a new sub window. And I go back to the direct plot form, click plot. Okay, so on the right hand side, this is a new loop gain plot. And if we compare them, that's obvious. See, the phase starts to drop earlier. Does that make sense? The phase starts to drop in the original case at this location, which is around, let's see, 50 kilohertz. And now on the right hand side, the phase starts to drop around 470 hertz. So the dominant pole frequency has been reduced. Does that make sense? And another way you check this is you can look at the magnitude. So where is the location of the first pole? Probably it's gonna be here, right? Starts to drop. And the first pole frequency is 350 kilohertz. And now, after adding the compensation capacitor, the first pole frequency is reduced to 700 hertz. Does that make sense? 700 or 600, something like that. And another thing is, actually, if you are more careful, you can find out the second pole location, and it turns out the second pole frequency will be increased, and this is called pole splitting, how we compensate for two-stage amplifier, right? And another very interesting thing is, look at this. What's happening here? Look at this, at this location. If we only have a second pole, then the slope will be bigger. At the second pole, the slope will be changed to negative 20 dB per decade to negative 40. Does that make sense? But now, the slope doesn't drop. This means we have a zero here, right? And this zero actually is bad for frequency compensation. So our next thing is, so now let's remember, with this setup, our phase margin is pretty much around 70 degrees, right? Let's play around. Let's add another resistor to play with the zero. So I'll add a resistor. And on the lecture note, it says that in order to move the zero to infinity, then the resistance should be close to 1 over Gm of this guy, of this transistor, right? So let's try. I'll go to result, print, this operating point. I'll select this transistor to figure out the Gm. The Gm is around 400 micron. If the Gm is 400 micron, then 1 over Gm will be, let's see, maybe 2 kilo ohm. Does that make sense? 1 over 400 micron, which is 2.5 kilo ohm. So I'll change the resistance to 2.5 kilo ohm. Click OK. And simulate it again. Go to result, direct plot, main form. The phase margin now is 85 degrees. So we have a better phase margin. Does this make sense? And we can also plot the loop gain. So let me add another window. And let's plot the loop gain. Loop gain, plot. Okay, so what's the difference? Here, at least, the zero is less significant, right? Okay, and this looks like to be a much better frequency compensation, because very obvious we have two poles, and the two poles, they are separated, splitted from each other. Because of this, we have the first drop then get saturated at 90 degrees, and the second drop. Does this make sense? Okay, and here we can't tell because the two poles, they are close to each other, so we can't tell this flat region, a saturation at 90 degrees, and originally this is a bad stability design, right? And eventually we get a very good stability, 85 degrees. Does this make sense? Okay, and the last thing we have to learn today is to analyze the frequency performance. The temperature performance. So go to ADE, and if you go to setup, temperature, you'll see the default temperature for this simulation is 27 degrees. 27 Celsius degree, which is room temperature, right? And unfortunately, the on-chip design, especially CMOS design, it's very sensitive to temperature. Later on, we will learn how to design temperature robust circuit based on band gap circuit. So, but now let's look at what's going to be the difference if the temperature changes. So, what we can do is we can now go to Tools, Parametric Analysis. So, besides the sweep on the frequency, I will add another sweep, and here I'll add the variable name TEMP. TEMP is a global variable in ADE, and it stands for temperature. So I'll sweep temperature from -40 degree to 100 degree, and I'll choose the sweep to be linear sweep. The linear step size will be 20 degree. Okay. After that, I go to Analysis, Start. This means the periodic sweep is sweeping temperature at each different temperature. It will simulate all the DC, AC, and the stability we have set up in analog design environment. Okay. So this sweep is finished. If this is finished, let me do this. I can go to analog design environment, go to Tools, Waveform. So if I do this, I added another waveform window. Okay. And now I go to Result, Direct Plot, Main Form, Stability, Loop Gain, Magnitude, and Phase plotted. So on the new window, you can see a family of curves, and each curve corresponds to a different temperature. Does this make sense? Okay. And I add another sub window. Add another sub window, and I change the plot to phase margin. And now I don't have the number of phase margin shown here because I have different temperatures. At each temperature, I have a phase margin, right? So I have to plot a phase margin. So the second plot is phase margin as a function of temperature. Does this make sense? Okay. So as we can see, if the temperature is increased, the phase margin gets smaller, right? So in for analog designers, it doesn't mean we design something with the original setup, then that's finished. We have to worry about temperature corners. Like in this case, the real design we have to worry about is a case at 100 temperature, which is the most challenging one, right? And likewise, you can also change the process corners. So you go to Model Library, you can disable the original typical process corner and choose another process corner. For example, I can disable this, and I'll go to Browse, Model, and I'll use NFF typical, which stands for fast process corner for NMOS. And I'll choose for PMOS, I'll choose PFF. So now we are simulating when the process variation go to the situation that the process is the fastest, okay? Then click OK. And try to run the parametric simulation again. Do I have the parametric analysis? Temperature from -40 to 100, and the step size will be 20 degree. Go to Analysis, Start. Okay, when this is finished, let me see, where is my waveform window? Okay, on this waveform window, I want to add another plot of the phase margin. So go to direct plot, main form. And plot the phase margin. Okay, so let's see. At a different process corner, the phase margin will be different, right? So at different process corners, you also have different phase margin. So eventually, when you design something, you have to exhaust all the temperature possibilities combined with all the process corner possibilities. And what's worse is they normally call this PVT corner, and you also have to combine it with the supply voltage corner and find out what is the most challenging case. Okay, all right. So I think basically this is what we have on EDA tutorial number 2. Do we have any question? No? Okay, great. Then I'll stop here. Thank you. I'll see you on Thursday.